Hey everyone, today we're going to pull back the curtain on one of the most powerful and kind of sneaky optimization techniques in the world of AI, mixed precision computing. It's the secret sauce making our AI models faster, smarter, and way more efficient. So yeah, let's just dive right in.
Okay, so let me start by asking you a question. What if you could basically double the power of your AI without having to buy a single piece of new expensive hardware? I know, it sounds a little too good to be true, right? But that's the core promise of what we're talking about today. To really get why this is such a huge deal, we first need to talk about a major headache in AI development today, and that is the resource problem.
So here's the thing. The AI models that we rely on for all this amazing stuff, well, they are absolute monsters when it comes to resources. They need massive amounts of memory, they take forever to train, and they just burn through electricity. The very thing that makes them so accurate, their numerical precision, also makes them incredibly slow and expensive.
But what if we could be a little bit smarter about how we play the numbers game? Well, that brings us to this really elegant solution, mixed precision computing.
So what is it exactly? At its heart, mixed precision is all about being strategic. Instead of using super high precision numbers for every single little calculation, it mixes and matches. It uses those heavy, super accurate numbers only when they're absolutely necessary, and then uses lighter, faster numbers for everything else.
You know, a great way to think about this is like having a toolbox. High precision, what we call FP32, that's your sledgehammer. It's incredibly accurate, super powerful, but it's slow and heavy to swing. On the other hand, you have your low precision formats. Think of these as a fast, light hammer, perfect for getting most of the job done way, way faster. And we can break down that toolbox even more. You've got your 32-bit sledgehammer, that's the traditional standard. Then you've got a couple of 16-bit options. FP16 is super fast, but you have to be careful with it, while BF16 gives you a much better balance between speed and stability. And then there's INT8, the fastest of the bunch, which is awesome for running models after they're already trained. So how on earth does the system juggle all these different tools without totally tanking the quality of the final model? Well, it's a surprisingly clever little process.
It's basically this beautiful three-step dance. First, most of the data, things like the model's weights, which is its learned knowledge, gets stored in that fast, lightweight 16-bit format. But, and this is the really clever part, to stop rounding errors from piling up, the internal math is still done in the high-precision 32-bit format. And most importantly, the system always keeps a high-precision master copy of the model's weights on the side, so none of those tiny, crucial updates from training ever get lost. Now, the reason this whole juggling act actually works comes down to a fundamental secret about AI. Deep learning models are surprisingly tough. They're resilient. See, neural networks have a ton of redundancy built in, so tiny little errors in one corner of the network usually just get averaged out by thousands of other calculations. They just don't need perfect, down to the last decimal point precision to learn patterns and make good predictions. And when you realize that, the real-world impact is, well, it's staggering. We're talking about making AI fundamentally faster, cheaper, and bigger. I mean, just look at this. The time it takes to train a massive AI model can literally drop from weeks down to just a few days. That isn't just a small improvement. That's a total game changer for how fast people can build and test new ideas. And it gets even better. Because those lighter numbers use half the memory, the math is really simple. You can literally fit an AI model that is twice as large, twice as powerful on the exact same piece of hardware you already own. This isn't just theory either. This stuff translates directly into things we use every single day. It means faster, more natural responses from your voice assistant. It means powerful AI can finally run right on your phone instead of needing to connect to a giant server in the cloud. And for businesses, it means huge cost savings. Less hardware, less time. It all adds up.
But, of course, there's no such thing as a free lunch. This incredible power comes with a few really important trade-offs that you have to know how to manage.
You definitely have to be careful. There's a risk of what's called numerical instability, where numbers can just blow up and get too big or vanish into being too small. You also need the right gear. This really shines on modern GPUs that have specialized hardware called tensor cores. And finally, you always have to test your final model carefully to make sure there wasn't a meaningful drop in its accuracy. You know, this quote really just nails the entire philosophy in a nutshell. It's not about getting rid of precision entirely. It's about being smart, being strategic, and using the right tool for the right job at exactly the right time.
And that kind of leaves us with a final, bigger question, doesn't it? As our AI systems get more and more efficient, we're faced with these trade-offs. In a world where we can trade a tiny, tiny fraction of precision for a massive gain in speed and efficiency, how do we decide when good enough is actually good enough? That's a question that's only going to get more important as AI keeps evolving. Thanks for joining me.